NTU method in heat exchanger analysis. Okay, so for us chemical engineers, this method is a really powerful tool. You know when you need to analyze a heat exchanger but don't know the exit temps? Well, this lets you bypass all the complex, iterative calculations of the older LMTD approach. It's a lifesaver, honestly. So how does it work? It all comes down to 3 core ideas. First, there's effectiveness. Think of it as a grade for your exchanger. It's simply the ratio of the heat it actually transfers versus the absolute maximum heat it could theoretically transfer. Simple as that. Second is the capacity rate. Now, this is just the mass flow rate times the specific heat. The key here is we always focus on the minimum capacity rate, or Cmin. That's because this is the fluid that undergoes the biggest temperature change, and it's what limits the maximum possible heat transfer. And finally, we have the number of transfer units, or NTU. Just think of NTU as a measure of the heat exchanger size. It's the product of the overall heat transfer coefficient and the area, that's UA, all divided by that Cmin we just talked about. It's crucial for comparing and selecting different exchanger types. So these 3 variables, effectiveness, capacity rate, and NTU, allow you to analyze heat exchanger performance explicitly, without any iteration. Let's dive into more detail.
All right, let's dive into a really powerful tool for analyzing heat exchangers, the effectiveness NTU method. Ever been stuck on a heat exchanger problem because you don't know the exit temperatures?
Yeah, it's super common.
The usual LMTD method can get you stuck in a frustrating loop of just guessing and checking. Ugh!
So there has to be a better way, right? What if you could just calculate it directly? Okay, let's get into it. This is the effectiveness NTU method, and it avoids that whole guessing game.
It's a total game changer, especially for comparing different heat exchangers for a specific job. So first up is effectiveness. We use the symbol epsilon, and it's basically a performance score. The formula is pretty simple. It's just what you actually transfer divided by the most you could possibly transfer.
So that top number, Q actual, is what's really happening. The heat your system is actually moving.
And the bottom number, Q max, is the theoretical limit. Think of it as the perfect scenario.
Now this is cool. That maximum transfer is actually limited by the fluid with the minimum heat capacity rate. This fluid is the bottleneck. It's the one that dictates the absolute maximum heat transfer possible.
And this is why it's so great. With effectiveness, you can find the temperature change directly, no iterating.
Okay, but what about the exchanger itself? How does its size and design play into all this? That brings us to our next key term, NTU. Just think of it as the exchanger's power level.
The formula for NTU is where the physical design comes in. It's UA divided by Cmin.
The top part, U times A, is its total conductance. That's the overall heat transfer coefficient and the area.
And we divide that by Cmin, that same limiting fluid we talked about just a second ago. Basically, a bigger NTU means you've got a more powerful heat exchanger for those flow conditions.
So the two are totally linked. If you know the NTU, you can figure out the effectiveness, and vice versa.
So why is this method so awesome? Well, you can skip the guesswork and compare different designs easily. It's an amazing tool for analyzing what you have or for designing something new and way more efficient. So with effectiveness and NTU in your back pocket, what heat exchange puzzle are you going to solve first?